In a previous video, I had repaired this particular device. It's a Datong D70 Morse code tutor. And you switch it on, and it plays Morse code at you. Now, these devices are used for learning Morse code. This was built in around 1980 or early 80s or late 70s. And I'll put a link in the description for the repair video that I did on this. But one of the viewers of that video very kindly asked if it's possible to make a modification to this to change the way that the letters are delivered. So for example, by default, this provides 5-character words. So you'll have 5 letters or 5 numbers or a mixture of letters and numbers, but it's always 5 characters, and then there's a space. It's kind of like a word block, 5 characters, a space, 5 characters, and a space, and so on. And that becomes a little bit repetitive and predictable for learners of Morse code. And so the idea is, can you change the length of those characters to provide some uncertainty, a bit more challenge? It's a bit more realistic to the kind of conversations you'll have when using Morse code on the air. Now, the viewer very kindly offered an idea that he thinks he saw a modification somewhere in the past. It might have had an RC circuit involved. He couldn't remember the details. So I took a look at the circuit to try and figure out if I could reverse engineer the same thing. So can we create a modification to this particular example where we have not just 5 words, 5-character words, but 2 words, 3 words, 5 words, 6 words, 7 words, whatever. I won't labor the point as to exactly how the circuit works, but the highlights are that you have a master clock up here, you have your power supply and audio chain over here, you have the programmable read-only memory, 32 address memory, which holds all 36 symbols of 26 letters and 10 numbers, and that's quite a nice little bit of engineering. But essentially from here, you have the way to actually execute those letters. They're pushed to 2 chips here. This is a counter, and this is a shift register. The information is stored as 8 bits in each address, so each letter and number is 8 bits. 3 bits explain the length, the number of dits and das, or dashes and dots, in the representation of that character. And this shift register actually looks at the actual dots and dashes itself and sends them individually up to the audio chain for execution so you can hear them. Now, the important thing about these circuits is you want to have some randomness, some variety of the letters coming at you. And that randomness is provided by this jittery, noisy clock, which is separate to the master clock. And this one provides a square wave, which runs another counter essentially down here, and this one cycles through all the possible address numbers. And when you want to get a letter, this circuitry here wakes up the memory. The memory looks at the inputs, finds an address number, for example 23, and then we'll look at the address contents at address number 23 and put the details, those 8 bits, on the output pins. There's a slight delay in reading those pins, which is brought together by this RC network here. And that delay allows the memory to switch on, find an address from the counter, and expose it to the pins. And then these 2 chips load. They read the output from the slight delay, and then they execute. Now, as those letters are being executed, every time you call this process for a new letter, this little channel over here, this link, goes to this chip here, which is a decade counter. And it's this chip which counts the blocks of 5 letters. So every time you get a new letter, you get a pulse on the clock pin here, and this counts up by 1 to count to 2, 3, 4, 5, and so on, to count the blocks. Then it will, at the end of 5 letters being sent, it triggers this pin, and it basically blanks the output. No matter the next letter being ready to be read, it blanks it, and a default circuitry sends us essentially an interword space, a dash and a dot. And then the whole thing cycles back on again. This counter resets to start counting 5 letters or numbers, and the cycle repeats. So really, we want to try to influence this chip in how we can change this default five-character word. Looking at this chip in a bit more detail, we see that it is a CD 4017, which is a decade counter. And if you look at the data sheet, you can find out the schematics here. Clock and a reset pin and the output pins for the counter. There's also a pin called clock inhibit. And I think that is an interesting pin to look at. So essentially, we can see that clock inhibit is pulled low. It's tied to ground, which means that every clock pulse that comes into this chip is counted. But the clock inhibit pin, if it's ever high, when a clock pulse comes in, the counter does not advance. It does not move forward to achieve a higher increment in the counter. So that's an idea to explore, to see if we can change the length of these word groups. Say, if one idea that I'd like to explore is to take a clock pulse and put it in here. So it's high and low, high and low, high and low. And indeed, if we use the random pulse, which is not, well, I call it random, but it's a bit noisy. The frequency, sometimes it cycles faster and faster and slower. That irregularity can be used to be fed into the clock inhibit. And when that clock is high, any new letter count into here will be ignored. And so you'll just get an extra letter for free. And when this clock goes low, then you'll advance the counter and move it forward. So that's a way of altering the length of the counting. And that's exactly what I've got displayed on the scope. The yellow trace is every time there's a letter coming through, we get a pulse. That's that pulse, that yellow trace there. If I turn it up, you can see that it's triggering basically on every letter that's being sent. And that is the space. There's a letter space that's not audibly heard, but it does cause a pulse. There. And that pulse is the silent pulse, which gets the counter to 1, which then drives these things to deliver a silent space. Now, let's compare that clock, so that pulse to the clock. And that's what I have set up here on channel 2. So you can clearly see this blue square wave, which is the noisy clock, and it is irregular. You can see longer spaces, shorter spaces, and so on. But there is some synchronicity with the pulse in the clock that we're interested in. Sometimes they're aligned, and sometimes the noisy clock happens earlier. Here, for example. To make it more clear, let's put the math channel on. And the math channel is the noisy clock minus the pulse for counting the numbers on the chip. So when this is high, like here, we see the clock precedes the pulse. When it goes low, here, they're in sync. And sometimes you'll see a negative, like there, where the clock pulse actually preceded the count pulse precedes the clock pulse. Now, what I've observed is that this pattern is not regular, it's not repeating. So it does provide some variability. Now, this is important. You need to have a clock pulse before the character counting pulse. So this pulse in the clock inhibit channel has to happen before the clock pulse. And the reason for that is explained in the chip diagram. What we can see, if I zoom in on an example of the clock, when that clock, every time this pulse happens, we get a new letter, okay? And that's coming from this is the way we're counting our letters. And every clock pulse is incremented inside the counter. And then when we get to 5, in this case actually it's pin 6, we hit the reset and we go back to 0 again. But when you have a clock pulse going to 1, another clock pulse going a clock pulse going to 0, then a clock pulse going to 1, but then you see that if the inhibit pin actually happens before the rise time of the clock pulse, that clock pulse is ignored, and you still don't advance the counter. You're still stuck on 1. So that's important, because these chips, when they measure the clock pulse, they're measuring the rising edge of the clock pulse, and they do so very accurately. So as soon as you get a rising edge, it will count the extra letter. It doesn't really matter how long the pulse is, it's the rising edge. So to inhibit that, you need to have the clock inhibit pin high before that rising edge. And that is what we're trying to find inside the circuit. And that's what I'm hopefully showing you here. That when this noisy clock, this blue trace, is happening before the clock pulse, before that yellow rising edge, and it's probably more cleanly shown here, is when this red trace is high, that's exactly what happens, then that could activate the inhibit channel and prevent the counter from counting this pulse. So long story short, I think there's a way, if we tie this clock pulse to the clock inhibit of this counter chip, we have the right leading edge, or if you like, not the leading edge, the sort of an slightly advanced high level that is before the leading edge of the clock pulse to prevent this chip from counting it. So what does that mean? Well, it means that we have a way of creating some random variation in counting using a set word group of 5 letters. So it could be 5 or 6 or 7 or 8 or whatever it is letters in the word group. Now, the question is, if you wanted to change that to smaller word groups, suppose you want to start counting at the 2s and 3s and 4 length word groups, then you could change the reset pin and not tag it on the word groups of 5, but tag it on word groups of 2, for example. Just change this connectivity. So then the default counting would be get word groups of 2, 1, 2, reset, 1, 2, reset. But with this advanced variation, you could get word groups of 3 and 4 and 5 extra letters before you finally use up all the official counts to get to 2, for example. So there's a way of doing that. So the next step of this video is actually to try and put this into practice and see if we can get word groups of 2, 3, 4, 5, 6, and so on. Okay, so I've located pin 13, which is the clock inhibit pin on IC4. And you can see how it was tied to the pin 8, which is ground. I just pulled back the solder mask and broke the trace, and then I just tacked in a bit of wire. And we'll connect that up to the noisy clock and see if we can get some changes in the word length. And just as you're about to switch it on, the cable breaks on the speaker. I'll have to put that back together. Nine. 8. 15. So clearly, this connection, all I've done is run a jumper from the noisy, where is the schematic, from the noisy clock to the clock inhibiting pin, and you change the length of the word group. I did some analysis. So basically I let it run and I counted the number of letters. You can see there's 10, 11, 10, 15, 13, 9, 14, 6, 9, 13, 6, and so on. So obviously quite long, in some cases even 22. And that's assuming that you have a default 5-word group or 5-character group. And I guess you can think of it by multiplying it. So if your base word is 5 characters long, then the scale factor was twice as long, 3 times as long, 1.2 times as long, and so on. So maybe with this method, you would want to change the default word length to something like 2, and that would give you, you know, smaller words, 2s, 3s, 4s, maybe 10s, maybe, and so on. What's interesting is if you unclip it, so now we're not doing anything with this inhibit pin on IC4, it's floating. Listen what happens. One, 2, 3, 4, 5. So it seems that even if it's floating, the chip can think that it's grounded. Of course, occasionally it might randomly pull up and have a high voltage and therefore extend the word length a little bit more. So this hack seems to work. And so I guess the next step is perhaps to change this from a 5-word group down to, let's say, a 2-word group, and see how long the words are. Okay, just like the previous tack wire that I put on pin 13. Pin 13, I just broke the trace and then tacked a wire that I could use to connect to the noisy clock, which is what you see here. I did the same thing. I broke the trace between the reset pin and the 5-word group counter, which is pin 5 here, which is actually counts to 6. I broke that trace, tacked in a wire on pin 15, and what we'll do is we'll stick this on another pin that generates a word group. Maybe we'll try the 3-word group. And to generate a 3, you've got to connect it to pin 7. Okay. So let's see what happens if we can get shorter word variations. So I'm going to connect pin 7. Seven. Oh, came off. Try again. 2. 4. 3. 2. 2. 5. 5. 2. 5. 2. 8. Okay, so it looks like if you, yeah, I mean, for as a training tool. You could pick whichever pin you want, and if you really wanted to, you could put a switch in and just select all these kinds of pins, kind of like a dip switch or something, or jumpers. Yeah, if you break the reset pin and stick it on pin 7, which gives you a 3-word default, with the clock inhibit pin getting high load from a jittery clock, you can extend that 3-word default to 4, 5, 6, 7, 8 letters, whatever it is. Interestingly, it could produce 2. I'm not exactly sure why it would produce 2. But I probably would wire that in. So I think I'll just draw this video to a close. I've proven that you can make a variety of word length groups really with no extra components other than connecting the existing noisy clock to the clock inhibit pin and not connecting it to ground. So we break that trace. And break this trace from the 5-word group to I guess, pin 7, which is the 3-word group. And then have a go. I guess the way to resolve this would be to, probably what I'll do in the, I won't show this, but basically take a double pole or 2-pole, 2-throw switch, double pole, double throw switch. And I'll probably use, well, I'm not going to, this is for the headphones. This is for connecting a key to drive the tone. I'm never going to do that. I have a nice tone generator elsewhere. But I can use this hole to pop a switch in. I'll take this out. And then you're going to wire those 2 center points to pin 13, clock inhibit, and pin 15, reset. You throw it one way. Say the top 2 pins will take you to ground and pin 5. Which is basically this. If you throw it the other way, the bottom 2 pins will go to the noisy clock and maybe pin 7, which just gives you the 3-word groups. Throw the switch and you can have default 5-word groups and whatever else you want. So that's how you would mod a Datong D70 to create a variety of character groups. Thanks for watching.